Hey everyone, it's me here from my channel. And in this video, we're going to be talking about Newton's third law of motion. Action and reaction are equal and opposite. Now this is one of those laws that people tend to think they understand. But then when you ask them to explain it or to apply it to a situation, they often get it wrong. So if you want to make sure that you really understand this concept, stick around for the whole video and make sure you do the quiz at the end. See how much you learned. Alright, let's go ahead and get started. Okay, so Newton's third law of motion states that for every action there is an equal and opposite reaction. Now let's take a look at what that means. We'll start out with a simple example like these two people here who are pushing against each other. This person pushes on this person with a certain amount of force, and as a result of that contact, the second person pushes back on the first person with an equal amount of force. So the forces are equal and they're opposite. Now since the forces are equal, what happens? The people don't move. They're not moving relative to each other because the forces cancel each other out. However, if one of these people was more massive than the other, say this person over here was much more massive, then what would happen is this person would feel a smaller force and would move backwards. So even though the forces are equal, if the masses are different, then the acceleration of the objects will be different, and therefore they'll move differently. Okay, so there was an example of Newton's third law in action where the forces were equal and opposite, but the objects didn't move. Now let's take a look at another example where the forces are equal and opposite, but the objects actually do move. Here we have a rocket ship taking off into space. The rocket is pushing down on the ground with a very large force. That's the action. And the reaction is the force that the ground is pushing back up on the rocket. Now the reason that the rocket moves upwards is because the force that the ground is pushing back on the rocket is larger than the force that the rocket is pushing down on the ground. So even though the forces are equal and opposite, the net force on the rocket is downward. So it has a non-zero resultant force acting on it, and therefore it accelerates upwards. Alright, now here's something that can be confusing about this. A lot of times people think that these forces, the action and the reaction, happen at the same time and they're on the same object. But that's not necessarily the case. Like in the rocket example, the action is the rocket pushing down on the ground, but the reaction, the equal and opposite force of the ground pushing up on the rocket, that's not happening at the same time. There's a little bit of a delay. The rocket pushes down on the ground, and then the ground has to rearrange its molecules and particles and exert a force back upwards on the rocket. So the action and reaction aren't necessarily happening at the same time. And they also aren't necessarily on the same object. And this can get even more complicated. Like in the rocket example, the rocket is made up of lots of molecules, and all those molecules are pushing down on the ground. But the ground is pushing back up on the rocket, but not on every single molecule. It's just pushing up on the bottom of the rocket. So it is really important to keep in mind that the action and reaction forces aren't necessarily on the same object. They're onto separate objects. And the fact that they're equal and opposite doesn't mean that the objects don't move. Okay, so now let's talk about momentum. If we have an object with some mass moving with a certain velocity, it has some momentum. And momentum is defined as the mass times the velocity of the object. Now if we have two objects, then the total momentum of the system is just the momentum of object 1 plus the momentum of object 2. Now here's where things get interesting. If we take the rocket example again, we have a rocket of mass m1. Now the rocket continues to accelerate downwards, increasing its momentum. So the Earth must increase its momentum to keep the total momentum of the system at zero. In other words, the Earth must speed up. Now you might be saying, well, the Earth is so massive, it won't speed up very much. And that's true. The Earth does speed up a little bit, but it's such a massive object that it only speeds up by a tiny amount. But nevertheless, the Earth does speed up. So what does this mean for Newton's third law? Well, Newton's third law says that the action and reaction forces are equal and opposite. And we know that the force of the rocket pushing down on the Earth is equal to the force of the Earth pushing back up on the rocket. But what we've shown is that the effect of these equal and opposite forces isn't equal. Why not? Well, because the rocket and the Earth aren't just objects, they're really systems of molecules. And the rocket and the Earth are made up of different numbers of molecules. Therefore, they have different masses. So what we've shown is that for every action there is an equal and opposite reaction. But the effect of those forces isn't equal. You might be wondering, wait a minute, if F equals ma, and we know that the forces are equal, shouldn't the accelerations be equal as well? Well, they would be equal if the masses were equal. But the masses aren't equal, so the accelerations aren't equal. In fact, the acceleration of the rocket is much larger than the acceleration of the Earth. Okay, so we've looked at a couple examples of Newton's third law. But here's another one you might have seen before. A person swimming. As the person swims forward, he pushes the water backwards. That's the action. And the reaction is the water pushing back on the person, propelling him forward. Again, the action and reaction aren't happening at the same time, and they're not acting on the same object, but they are equal and opposite. Okay, so let's take a look at the math behind this. Now the person starts to push on the water. He exerts a force on the water for a certain amount of time, and that gives the water an impulse, which changes the momentum of the water. The total momentum of the system is still equal to the momentum of the water, plus the momentum of the person, since momentum is conserved. The person must gain an equal amount of momentum in the opposite direction that the water loses. So the person speeds up. But what about the water? It slows down because it gives momentum to the person. But the water is made up of molecules, and each individual molecule is speeding up and slowing down. What about the overall motion of the water relative to the Earth? Does that change? No, it doesn't. In fact, the water as a whole moves backwards just like it did before. This is because the forces that the person exerts on the water are equal and opposite to the forces that the water exerts back on the person. And the total momentum of the water plus the Earth is conserved. So the Earth moves forward along with the water. All right, hopefully those examples really helped you understand Newton's third law. If you want to test your knowledge, go ahead and take the quiz. Thanks for watching. I hope you learned something. If you want to keep learning, check out the next video.